Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this video we look at how to write logically structured explanations to problems that involve changes to chemical systems at equilibrium.
Okay, so what we've done so far then is to cover all of collision theory and all the background associated with it, and we've done the second part of the course, which is about equilibrium, as you know. What I wanted to do then is to look at how we break down an answer for equilibrium, where we look at a change to a system and see how we go about writing those answers by following a system of logic. And the nice thing is, both equilibrium and collision theory are what we call cause and effect type problems. The cause is something that you change in the system. The effect is a consequence of something that happens because you've changed it. And in between, you've got a theory or some explanation for it. So in the case of collision theory, you're using collision theory itself. In the case of equilibrium, you're using Le Chatelier's principle. So we're going to focus on equilibrium because that's what we just finished. But exactly the same sort of principle applies to collision theory. And I do have, and you've already seen, a set of problems associated with collision theory which I've broken down in the same way. So whatever we're saying about equilibrium today applies also to collision theory. Okay, it's a very similar type of approach. So in this one, what we've got is this reaction system here. And the following slides will use the same system, but we'll go on to look at different changes. So I'm going to write it up here so you can see what the system is without having to keep flicking back in your notes. It's on the board. And once again, it's nice if somebody can tell me, if we look at the value of Kc, what does it tell us and why? What does that value tell us? Well, the first thing to ask then, is that a big or a small number? Small. It's a small number. What does Kc tell you?
It's reactant favoured.
It's reactant favoured because Kc is the products divided by the reactant concentrations. Yeah. If this is a very small number, it's telling you you've got a low concentration of products, the top bit, the numerator, and you've got a very large number, the denominator, which in this case is the reactants. So in other words, equilibrium is favouring the reactants. It's way over this way, high concentration of this, relatively low concentration of that, small number. So it's a good start. So what it's asking us is explain what would happen for the equilibrium mixture if we first of all add extra gas. Now this is a cause and effect problem, so you need to start with the cause. Now this isn't really relating, this is telling you you're just adding gas. That doesn't tell you what we're doing to the system that's going to upset the equilibrium. What actually is the effect of adding N2O4 gas? What is that going to do? Which factor are we talking about? Concentration. So if we add this, we're opening the system up, it's no longer closed, so equilibrium will be lost, and we've increased this concentration. Okay? So that's our cause. So we need to say that to begin with. Okay? Then we need to apply Le Chatelier's principle, and then we need to say what the effect is. Okay? And that's what you've got to do now. So let's have a look at the answer. And you'll notice that I've slightly changed things around a little bit. So it's a little bit more concise. Okay? And I've said about equilibrium being lost and restored. Okay? So let's have a look at the starting point. And that is to state the change. Okay? So you can see clearly adding it increases the concentration. The highlighted bit is the bit that refers to the stating of the change. We've looked at what happens when you change concentration. And so by adding extra stuff in, we're actually increasing, in this case, a reactant concentration. Okay, so that's our change. The next bit is Le Chatelier's principle. Okay, so what the system does is it counteracts a change. If you actually look at a definition for Le Chatelier's principle, that's a word that often comes in. They actually call it a constraint, but I don't think it's a constraint. It's quite the opposite. It's unconstraining something. And so the system here, the reaction system, counteracts the effect of that change. Okay? And it reduces the concentration because you've increased it. So it's just saying what it's doing as a counteraction, if you like, to the change you've made. So it's going to reduce the concentration by favouring the forward reaction. So favouring the forward reaction reduces the concentration of that reactant and increases the concentration of the product. That's what that means. Okay? And so that's Le Chatelier's principle applied in this scenario. So we've got our cause, we've got our bit of theory in between. Now we have to look at the effect. Okay? And the effect is that equilibrium is going to shift this way. If you're favouring the reaction, the forward reaction, then you're going to shift equilibrium in this direction, and so you're going to increase the concentration of products and decrease the concentration of reactants. And that's probably what you want to do, because if you put it in this direction, we put it out in this direction, we want the product. And what this is telling us is we ain't going to get much of it to begin with. So one way of increasing the concentration of the product is to add some more reactants in. So what you're doing is you're just unbalancing equilibrium. It's coming back to equilibrium. So you've unbalanced it by putting far more product in. No longer at equilibrium, it's got to restore it. And so the way it restores it is getting Kc back to its original value. So it's got to, you've pushed up the reactant concentration, it's got to pull them back down and push up the product. And it gets back to Kc, as it was originally, so it's back at equilibrium. So it's losing equilibrium, then restoring it. Okay? Down here. So that last bit there is the actual effect. So cause and effect, with a bit in between. And that's, as I say, the same for collision theory. When you change the concentration of something, you could say that's adding something's increasing the concentration of something. Then you're going to increase the frequency of collisions, which increases the effective collision frequency, and that speeds up the reaction. So you'd be using exactly the same structure, but in a different context, because it's still a cause and effect type problem. What you've got to work out often, because they're not going to be helping you in the way when the examination comes along and saying, oh, we're going to increase the pressure, we're going to decrease the pressure, we're going to increase the concentration, we're going to decrease the concentration. They'll actually say what you would do in practice. So in industry, they don't just increase the pressure, they have to do it in a particular way. And one of the ways you can do that is by changing the volume of something. So if you actually make the volume smaller, but have the same reactants there, so you don't let anything in or out, but you make it smaller, then you've got more, the same number of particles in a much smaller volume. So that's basically going to increase the pressure, because the collisions on the surface area, which is now smaller, are going to be increased. And so the pressure goes up. So halving the volume doubles the pressure. So this is a pressure problem. Anything where they change the volume of something is going to be a pressure problem. Okay? I'll put the reaction up here. See if you can do this one. As I say, very quickly. Try and use the wording I just used. Okay. So, here's again the answer. Again, it's about the same sort of length of answer. These things do. And it's all pushed on one side in very large font, so it seems like it's a lot. But handwritten, this would only cover a few lines. It's not going to take all of a page up. Okay, so it doesn't require an enormous amount of writing. So once again, say what's being changed. So decreasing the volume means you've increased the pressure. Okay? So that's the change we've made. And so the system counteracts that increase by by decreasing it. And the only way it can do that is by reducing the number of particles in a system. Remember, if you want to increase the pressure in, say, a tyre, you blow it up by putting more air into it. Okay? What we've done here is increase the pressure. The only way we can actually decrease that pressure within the system without letting things in and out is actually having fewer air particles. So reactant particles, fewer particles, not reactant particles, but fewer particles. And so what you need for this to work is a reaction system where the number of particles on the reactant side is not equal to the number of particles on the product side. So we're going from one particle to two. So if we go in this direction, if we favour that direction, the forward direction, you increase the number of particles in the system, which increases the pressure. So increased pressure. If you favour the reverse reaction, on the other hand, you're going from 2 to 1. Fewer particles in the system, as more and more goes on. Okay. So that reduces the pressure. So you have a mechanism, provided these numbers don't equal each other, of either increasing or decreasing pressure. What we're saying here is the change we've made has increased the pressure. It's going to counteract that by reducing the pressure. It's got to reduce the pressure to get back to equilibrium. And the only way it can do that is favour a reaction direction that produces fewer particles, reduces the number of particles in the system so the pressure goes down. Okay? And so here we look at our reaction, it's the reverse reaction, we're going from 2 to 1. Okay? So you've increased the pressure, it's going to counteract that by favouring the reverse reaction where you're going fewer particles from products to reactants, it decreases the number of particles, so that reduces the pressure. Yeah? So it does that, and that's our Le Chatelier's bit. Okay? So just this bit here is Le Chatelier's principle. Okay? We've identified what's been changed. It's going to counteract that change by favouring the reaction direction that reduces the number of particles in the system. And then you've got to say what the effect of that is. So having done that, you've favoured this reaction, it's telling you equilibrium is going to shift that way. So this concentration is going to go down, this concentration is going to go up, and that answers your question. So that's the effect. Cause, theory, if you like, and effect. Try that one. Okay? Now I'm not going to break down these anymore. We will, but I'm not using all the fancy colouring. Have a go at that. This is new. The first one, there you go. So the first thing in the first sentence that I've said is what's the effect of cooling? Cooling is removing heat energy. That's the factor that's affecting the equilibrium, is the removal of heat energy. Okay? So the system counteracts that by favouring the forward exothermic reaction, which actually creates more energy. Remember, exothermic reactions give out energy. So if you're removing heat energy, you're going to favour a reaction that actually gives out more. So you take it away, it produces more. Okay? So the cause is heat energy is removed. The response, or the counteraction if you like, is favouring the forward reaction, which actually gives out heat energy until equilibrium is restored. So equilibrium shifts towards the product. This is the effect. And so the concentration of H2 increases. Now, so that's the first bit. So it's the same cause and effect with a bit of Le Chatelier in the middle. The next thing is, unlike the pressure and concentration changes, changing the temperature does cause Kc to change. Those other two factors do not cause Kc to change. Okay, that's the whole point. In this case, Kc will change. Okay? And we've got to work out what happens to it. Well, what we have to do is just look here. Okay? We're going to favour the forward exothermic reaction. Forget what it's telling us is we're going to favour the forward reaction. So we're halfway to the answer. If we favour the forward reaction, what's going to happen to the concentration of products relative to reactants? What's going to happen to the concentration of products? Going to go up. What's going to happen to the reactants? So you've got products over reactants. What's going to happen to the Kc value? Goes up. Okay? So let's have a look at the answer. See how I do that? So I've just repeated what I've said there. It favours the forward reaction. The concentration of products increases relative to the concentration of reactants. It's a very simple answer. Yeah? And you're saying Kc is products over reactants. So if this is true, then Kc goes up. Somewhere in your answer, write that. Then say whichever direction you favoured, what's it going to do to the products relative to the reactants? And that will tell you what's happened to Kc. Okay, so if you favoured the reverse reaction, the products goes down, the reactants go up, and so this gets smaller. In this case, it's the forward reaction that's been favoured, so that causes products to go up, reactants to go down. So Kc increases. Right, try that one. That's actually quite interesting. Okay, you don't actually have to use Le Chatelier's principle necessarily, but in a way you do, because you've got to work out what's going on to answer the second part. So the first part is a bit of calculation. Oh my gosh. So you've got to work out, given three concentrations, two concentrations, you can all three concentrations, work out the value of Kc. Okay. Can I add in an extra bit here? When you've worked out the value of Kc, tell me whether it's reactant or product favoured. Okay, so the answer is 14.5. And what does that tell you? Is it reactant or product? It's pretty much, there's significant amounts of each. Because it's getting quite close to sort of 1.
I thought that anything below 100 though.
Anything between 100 and 0.01, it's telling you you've got significant quantities of both reactants and products. Okay? If it was over 1,000 and below a 0.001, then you'll start to push it either way. But that's somewhere in the middle, so there's significant quantities of both. So what would happen if it was cold? What do you need to look at? What do you need to look at, first of all, before you can answer this question? What will you need to do? What's that called? The delta H value. What does that tell you? The forward reaction is exothermic. Okay? So you need to put that in pencil, I would suggest. Now, what does Le Chatelier's principle tell you will happen if you cool a system down? Because that's what's happening here. You're cooling it down. It'll try to generate more heat to warm it up. What type of reaction generates heat? Exothermic. So cooling it is going to favour the exothermic direction, which is the forward direction.
Wait, exo.
Gives out heat. That generates heat.
And then endo like
Absorbs it in. It gets cold. They get cold. Whereas exothermics get warm. Yeah? So you've taken out heat. It's going to basically generate more by favouring the exothermic direction.
The H value will become even smaller, even more negative.
No, the delta H value does not change. By definition, it's constant. What it's going to do is affect these concentrations. So if you're favouring the forward reaction, what's going to happen to the concentration of reactants? They decrease. What's going to happen to this?
Increase.
So Kc is what? Products over reactants, reactants over products. Which way around is it? Products over reactants. You're increasing the products, decreasing the reactants. So what's going to happen to Kc? Increase. Okay, so let's have a look at the answer written out. Okay. So what you're doing is removing heat energy. The system counteracts that by favouring the forward exothermic reaction to put it back. Okay, it replaces the heat. Equilibrium shifts to the products, which means the concentration of products increases relative to the reactants. And since Kc is products over reactants, cooling causes Kc to increase. Don't forget to answer the question. What happens to the value? Right, can I move on to the next one?
1 second, the last sentence.
Right, try that one.
No, we've only got 2 minutes.
I think 1.5 minutes.
Yes, well, you can answer this in 3 minutes.
No, we've only got 2 minutes.
Come on, do this one.
Right.
You don't have to copy the question down, but we haven't done one of these. We haven't done this yet. Try it. So what is it we're trying to do here? A catalyst. What's the effect of a catalyst on a system that's in equilibrium? None. It'll actually make the system reach equilibrium faster, but it has no effect on equilibrium. So say that it's a catalyst. Often that's what they're doing. They're just asking, what is the purpose of that? And then write the answer. So, it speeds up the forward and reverse rates equally. So it has no effect on the position of equilibrium. It just means you get there faster.